Okay, so we're gonna first draw the circuit for t less than 0. And that's gonna look like this. And as you know, with capacitors, after a long time, at steady state, they become open circuits, right? Do you see anything wrong with this circuit? Yeah, right. Isn't this a bit of a contradiction, if you will? You have a current source with 50 milliamps, and you have an open circuit. And by definition, open circuits tell you that there is zero current flowing into it. So something's going on, right? Something's not right, okay? This is where you have to handle it a little bit differently than normal. So that's kind of how I identify when I run into one of these edge cases, right? I put my capacitor or my inductor in steady state, and if I have a current source in series with an open circuit, I know something's going on. So we're going to have to approach this problem differently. So I'm going to draw this capacitor, right? And let me just go ahead and define VC. Right? That's usually your first step. Choose the direction of your capacitor or inductor's polarity if it isn't given to you. So I'm going to choose it to be like that, which means that this is VC, and that is going to be IC. And we have to use this equation. IC is equal to C dVC over dt. Okay, now what we're looking for is VC of t, which means we have to solve for VC. And so in order to do that, we have to rearrange things. dVC is equal to IC over C dt. And then we are going to integrate this from 0 to t. We're going to integrate, which means we have to integrate this side from 0 to t as well. Because remember, we have to isolate VC, and we're solving for VC of t for t greater than 0. So doing the integral, we're left with VC of t minus VC of 0 is equal to, oh wait, sorry, I forgot one key step. I'm so sorry. IC, we know IC, right? We know the current through the inductor. What is it? 50 milliamps. So IC is 50 milliamps. And so what we're really integrating is 50 milliamps dt. And given this fact right here, the energy stored in the capacitor of this circuit is 0 at t equals 0. What can we say about VC of 0?
Can you repeat that again?
So the question tells us that the energy that is stored in the capacitor at t equals 0 is 0.
So VC of 0 is 0.
Correct. Right, and that comes from this equation. Right? If we were looking for the energy at t equals 0, which is also 0, right? Makes sense intuitively. No energy, no voltage. So that zeroes out, and we're going to be left with VC of t is equal to, 50 milliamps over 0.16 farads. 312.5 volts per second. T. Oh, millivolts. Right, because it's milliamps. Okay, now let me just kind of walk through that one last time, just so really hammer that down, right? So we're given the circuit and we're told that the energy stored at the capacitor at t equals 0 is also 0. And then it says that 2 seconds later, the switch is closed. Find Ix of 4s. And one more thing I want to write about this answer. This is valid for the following time interval, right? Because at t equals 2, the circuit changes, the switch closes. This equation is no longer valid. But between 0 and 2, it is valid, right? But to take a step back, right, what we're looking for is the following equation. Since the switch closes at t equals 2, this is our equation. Oops. Right, because we have a non-zero switching event, so we have to replace t naught with 2, which is where the following equation comes from. So what we're going to do is we're going to use this equation that we solved for VC of t for this time frame to find our initial condition. So that's exactly what we're going to do. VC of 2 seconds is equal to, I'm going to convert to volts, 0.625 volts. I just plugged in 2 for t. And I got our initial condition.
And circuits too are basically deriving the equation.
It's a different way to derive the equation for the voltage across a capacitor. Yeah.
But before we used it, they would just give us this.
They would just give it to us. Yeah. Now we have to use a little bit of calculus to kind of get creative to sort of hand derive that equation.
So in the calculator, did you put 0.3125 times 2?
Yes. Yeah. So I converted it to volts, and then you took 0.3125 times 2.
Okay.
Yeah. Divided by 1,000. Okay. Now, right. So that was step 1. Right. Was to find our equation. Step 2 was to solve for initial condition. Step 3 is now going to be to find our steady state condition. So we need to draw the circuit as t approaches infinity. In other words, after a long time, such that the capacitor is in steady state, so we can represent it as an open circuit. Now, do we see anything that is violating the laws of circuit theory here? Or is everything good? Yeah, looks good to me, right?
Yeah.
Nothing weird going on. All we need to do is solve for this voltage. We don't have any current sources in series with open circuits, and we have no voltage sources in parallel with short circuits. Those are your 2 edge cases. So we just need to solve for the voltage VC of infinity using standard circuit analysis techniques. So what would VC of infinity be?
I ain't never seen the TA, it's weird. Yes, we have to use because I haven't seen them.
All right. So VC infinity is going to be the voltage across which resistor? Let me frame it that way.
43 ohm.
Yes. All right. So VC infinity is going to be 50 milliamps times, by Ohm's law, 43 ohms. If we find the voltage across 43 ohm resistor, we have VC of infinity. We know the current through it, so we can use Ohm's law to solve for this voltage, which is 2.15 volts. Now we are going to redraw our circuit to find tau as seen by the capacitor. So we're going to replace the capacitor with terminals and find the Thevenin resistance as seen by those terminals. Right? And the current source becomes an open circuit as per rules of the REQ method, which means that this entire branch goes away and you're left with this circuit, the 43 ohm resistance. So obviously our equivalent is just 43 ohms. And so tau, which is RC, 0.16 farads times 43 ohms.
Wait, how did you get that circuit? What happened to the...
So I took this circuit right here, right, because the switch is closed. So this circuit essentially, and replace the capacitor with terminals. We have to find the Thevenin resistance as seen by those terminals. Since there's no dependent source, we can use R equivalent method. With R equivalent method, you deactivate all of your independent sources. So current sources become open circuits, which gets rid of this whole branch and leaves us with this circuit. And so tau is going to be 6.88 seconds. So putting it all together, VC of t is 2.15 plus the initial condition, 0.625, minus the final condition, 2.15, which gives you minus 1.525 e to the negative t over 6.88 seconds. And that's all in volts. And this is for t greater than or equal to 2 seconds.
This is negative t over 6.8.
Yes, negative t over 6.88.
So a lot of these problems are you're going to end up having two equations as your answers.
Mm-hmm. Even if there's a single switching event with no edge cases, with circuits 2, at the very least, they're going to tell you to solve for, some other value in the circuit, whether it be a current through something else or voltage across something else. And those voltages and currents are always going to be time varying naturally. Right? If you have a time varying voltage anywhere in the circuit, everything else is time varying.
On the 43 ohm because they're parallel.
Correct, yeah. And we're going to use that principle here again to find Ix of t, right? So step 5 is going to have us redrawing the circuit. This time I'm going to leave the capacitor as is. Oh, by the way, one thing I forgot to mention is I was wrong to say that we can choose our polarity here, technically. This curved line denotes the negative side of a capacitor. So technically this is the only way you can define the voltage. So sidebar, just remember that the curved side is the negative. So yeah, all right. Now let's finish drawing the circuit. All right. Let me define it like this. This is our VC. That's 43 ohms, 10 ohms, 50 milliamps. Okay. And we're looking for this current. All right, now who can tell me the equation for Ix in terms of VC?
Current divider? No.
We wouldn't.
Maybe VC
Could do-
divided by 43.
Positive or negative?
Okay.
Look closely at the.
Negative?
Yes. If you look closely at the polarity, right? You have a current that's entering the negative terminal of a defined voltage. So if you do Ohm's law, in terms of that voltage, since you are in active sign convention, it has to be negative. Ix of t has to be negative Vc of t over 43 ohms. So to find Ix of t, you just take our expression that we found for Vc of t, flip the sign, divide it by 43. Right? Which is going to give us negative 50 milliamps plus 35.5 e to the negative t over 6.88 seconds. That's also milliamps. And this is for t greater than 2 seconds. Okay, now last step is to just find the value of Ix at t equals 4. Ix of 4 seconds. So we're just going to plug in 4 for this equation. We're going to get 5 e to the negative 4 divided by 6.88. We're going to get negative 30.15 milliamps. Make sure that's good. No, okay. Something went wrong. Let's see if I can find it. Nah.
Are you following, like, making sense?
Kind of.
I just need to do some practice problems
Yeah.
so I can like
I'll
make
do
sure
that.
be able to like do all the steps like without
I need to do that.
seeing someone else like, put the steps before
When
me.
he's doing, I'm like, yeah, that's the correct way to do it. And I'm like,
Yeah, then like put like a blank problem before me. That's good.
and then
I'll
I'll be
blank
just
out.
as blank as the problem. Me too.
There's just like so many steps you have to like know, like, oh, I have to do this, this, and this, and this, and this, so that I can get
Remember
there.
how to explain this, the switches?
No, bro, I didn't. I didn't.
I heard a little bit when we were just talking about
Yeah, it's
2.15. R equivalent is 43 ohms. So 43 times 0.16. 6.88 seconds. And then we take that, Vc of t, 2.15 divided by 43, negative 50, 1.525 divided by 43, plus 35. Negative 50 plus 35. Oh, I see. See? It's so easy to forget it. The switch is not flipping at t equals 0.
T minus.
It was t minus 2. Yes. Okay, so this is negative t minus 2 seconds. That's why it's so important. It gives you the complete wrong answer if you don't do it. Minus t minus 2 seconds. Even if it's a single switching event, if it's not a t equals 0, you have to include t naught. So now if I take this equation and I do negative 4 minus 2, negative 2, yes, now I get negative 23.45 milliamps. The answer key says negative 23.5. So I'd like to think that's close enough. And yeah.